So, are you able to hear me?
Yes.
So, yesterday we were discussing about this concept, right? So, average power over a complete cycle. So, we discussed that average power is equal to ERMS into IRMS into cos phi. Is it right? Where average value is the product of the RMS value of EMF and the RMS value of current multiplied with the cos of the angle. 1 minute. Screen share is lost. Okay. Now, if the circuit is purely resistive, okay, if the circuit is purely resistive, then phi would be how much? Phi is basically the phase angle between the EMF and the current. Okay.
There will be no phi, so 0.
So phi will be equal to 0 degrees. Right. When it is 0, then what is going to be the average power? It will be ERMS into IRMS into cos phi. So it will be E divided by root 2 into I divided by root 2 into cos of 0 degrees, or E into I divided by, E naught into I naught divided by root 2. So E naught into I naught divided by 2 will be the average power. Is it clear? Okay. Similarly, when the circuit is purely capacitor, what is going to happen? Phi will be equal to pi by 2. Right? When phi is equal to pi by 2, average power will be equal to ERMS into IRMS into cos pi by 2. Answer will be 0. So the average power consumed by a capacitor in a purely capacitive circuit is 0. Okay. Similarly, when the circuit is purely inductive, then average power will be equal to ERMS into IRMS into again a cos pi by 2, which will be a 0. So what we can conclude from everything is that the value of power, the average power in the case of a purely capacitive and inductive circuit is going to be 0. I hope you guys are making a note of it. Right? Now see. So from this, what I can conclude is so I just wanted to tell you another term which is called as, okay, I'll explain it here itself. So if you observe the average power consumed by capacitive and inductive circuit. So average power consumed by capacitive and by purely capacitive and inductive circuits is 0. Okay. And this kind of a current where the average power consumed is 0 is called as watt-less current. Okay. So wattless current in an AC circuit is when average power consumed by the circuit in the set circuit is 0. So this current can also be called as idle current. Okay. Is this point clear? Yes or no? Are you able to hear me or not?
Yes, sir. Yes, sir.
Yeah. So it's called wattless current or idle current. Why did you come? Online lesson. Actually, we'll get to that. So we'll move to the next topic, that is transformer. So the next topic that we are supposed to discuss is called as transformer. So as the name suggests, right, transformer is that particular electrical device which converts low voltage to high and high to low. Okay. So can you give me an example where transformers are to be used? Can you give me an example where transformers are to be used? One is you would have seen outside your houses, a very big transformer and all those things. So what is the functionality of a transformer? Is basically to step down the value and give you an output. See, for example, let's say you have a plug point here. It's a 3-pin socket, okay, into which you connected your mobile charger. So the mobile charger is taking an input of 230 volt RMS value. Okay, and it has a peak value of 311. Okay, this 230 volt RMS value, what will happen is when it is coming to your mobile, if this 230 volt is directly given to your mobile, the first thing that you can see is your mobile bursting. So for that not to happen, what will happen is in your charger, there is a device used which is called as transformer. So what a transformer does is, it is basically an electrical device for converting, and transformer mainly works only for AC, does not work for DC. Okay, it's an electrical device for converting an alternating current at low voltage into that of high voltage and vice versa. Okay, means if you give a low input value and you get a high output value, you call it as a step up transformer. So low input is given and high output is expected, then this kind of a transformer is called as step up transformer. And when you give a high input and you expect a low output, then it is called as a step down transformer. told you both. Okay, let's see. So if I connect an AC source, okay, basically a transformer works on the principle of mutual induction. So it works on the principle of mutual induction, right? So when you have an AC source that is connected and it is mutually coupled with a coil. So the coil across which the AC source is connected is called as the primary coil, and the coil across which the load is connected is called as the secondary coil. Okay. So when they both are mutually coupled, what will happen is, depending on the number of windings that are present on either of the sides. So generally what will happen is the primary coil and the secondary coil will not have the same number of windings. Either of the side will be high, depending on what is your requirement, whether you want a step down transformer or a step up transformer. Okay. Now what can happen is, if you see the way they both are mutually coupled, their axes are parallel to each other. So whatever flux is getting generated here in the side of the primary coil, I wanted to get completely linked with the secondary coil. If it has to get completely linked, then what we do is we connect those windings with the help of a laminated iron core. So basically, use an iron core, whether it is a soft iron core or a hard iron core. That soft iron or a steel, we will see it later. But what is used? Iron core is used. And iron core can have lamination. So it is a laminated iron core that is used. Okay. So the first one is called as step up transformer, and the second one is called as step down transformer. So how to identify whether it is a step up or a step down by just looking at the diagram is look at the number of windings. If the number of windings are more for the secondary and less for the primary, you call it as a step up transformer. Okay, we'll prove that, don't worry. Similarly, if the number of windings in the primary is more compared to the secondary, you call it as a step down transformer. So whichever has more amount of windings will have more amount of EMF. Okay. So am I clear till this point? Everyone? Those are online. Am I clear?
Yes, sir.
Yes. Now, what is a principle? It works on the principle of mutual induction. That is, when a changing current is passed through one of the two inductively coupled coils, an induced EMF is set up in the other coil. Okay. Now, what is the construction for it? Basically, I told you already, a transformer essentially consists of two coils. What are they called? Primary and the secondary. Okay. The two coils are basically insulated copper wire, which have different number of turns, and they are wound on the same soft iron core. So if an iron core appears, it should be a soft iron core. Soft iron core means it has no hysteresis. In the sense, it has low retentivity. Remember, we discussed in the 5th chapter. Low retentivity and low coercivity. So these kind of devices are called as soft iron core. Okay. So the coil P2 is the electrical energy supplied is called as the primary coil, and the coil from which energy is drawn or output is obtained is called as the secondary coil. Secondly, to prevent the energy losses due to something called as eddy currents, what are those eddy currents? We'll discuss it. We use a laminated core. Okay. So because of, generally when you talk about an iron core, it has high permeability. So because of high permeability of soft iron, the entire magnetic flux that is getting associated with the primary coil will get completely linked with the secondary coil. Or else if this core was not there, what would have happened? Some of the flux would have got escaped in the air itself. So they're trying to control all the flux and pass it through the secondary coil so that you try to minimize the loss. You cannot make it 100% efficient, but at least you can make it 99 point something. Okay. So due to the current in the primary coil, as a result of which, what you can say is whatever is the flux that is getting generated by the primary coil will get completely linked. Theoretically, it will get completely linked with the secondary coil. Hence, you can say ideal situation is erased. Okay. So, this also prevents the stay currents being generated in the conductors lying around the consequent power loss. So, stay current, side length, whatever currents are unnecessarily getting generated will also be prevented because you're using a laminated. Okay. So, this is how the basic structural diagram of a transformer will look like. Please make a note of it. Done. Okay. So, how does it work? So, what is the primary coil connected to? It is connected to an alternating current. So, it generates an alternating magnetic flux. Accepted. Because alternating current itself will change its direction. When its direction is getting changed, then the flux associated with the primary coil will also change its direction. So, you can call it as alternating magnetic flux in the core. And this is being passing, this passes through the secondary also. Why? Because you're using a core, due to it, the losses are less. So this changing magnetic flux, according to Faraday's law, the changing magnetic flux which is occurring across the primary coil will induce an EMF in the secondary coil. And the EMF that is getting induced in the secondary coil will also be alternating. So what is happening is alternating current is generating an alternating flux across what? Across the primary coil. This alternating flux is linked with secondary coil. So this alternating flux that is linked with the secondary coil will generate an alternating EMF according to Faraday's law. Is it right? So when this is happening, then you can say one thing: if there is no leakage of magnetic flux, as I told you, there will be leakage, but you can at least try to make an ideal situation. If there is no leakage of magnetic flux, then the flux that is linked with each turn of the primary will be equal to that link with each turn of the secondary. Because whatever flux is getting generated in primary is completely linked with the secondary, right? So, what is going to be the mathematical expression for the relation between the EMF and the number of turns? I told you, right? The number of turns will vary, they'll not be the same. So, the theory is consider the situation when no load is connected across the secondary. Generally, when you take a load, it will have some resistance. So, when no load is there, it means you're taking the condition to be of zero resistance. So, no load that is connected to the secondary, that is, the terminals are open. Let N1 and N2 be the number of turns in the primary and the secondary coil, respectively. If that is the case, then can I say that the induced EMF in the primary coil is E1 is equal to minus N1 into d phi by dt? Can I say that? This is according to Faraday's law. Then what will be the induced EMF in the secondary coil? Minus N2 into the same d phi by dt. I didn't write it as d phi 1 by dt and d phi 2 by dt because it is the same flux that is getting linked with both. Am I clear? Is it right? Now what I can do is if I divide E2 with E1, E2 with E1, I get N2 divided by N1. This is going to be the mathematical expression for the relation of how the EMFs are related to the number of turns. Okay. Now, there is a small theory that is applicable. Let E be the EMF that is applied across the primary, that is the alternating EMF. Okay. Then, by Lenz's law, what you can say is there is a self-induced EMF that is going to take place. So, we discussed about self-induction, you remember? So, there is a self-induced EMF, E1, which is also called as back EMF. Why am I calling it as back EMF? Is because according to Lenz's law, the EMF that is getting induced within the primary coil due to its own flux will always oppose the cause. So, yeah. So, will oppose E1. So, what you can say is the resultant EMF in this case will be whatever EMF you applied minus whatever EMF that is getting generated due to self-induction. So, it will be E minus E1. Okay. Now, what will happen? This resultant EMF is the one necessary for sending the current to the secondary coil. Okay, even the primary coil for that matter. This EMF sends current I1 through the primary coil, and the coil is made of copper wire. The copper wire is going to have some resistance. Correct? So, can I write E minus E1 is equal to I1 into R? Can I say that? Okay. But generally, if you take the resistance of the copper wire that is used for primary and secondary, they have very, very, very small value. When they have small value, this parameter can be ignored. Then you can say E minus E1 is 0 or E is equal to E1. Now, what you can say, that is the reason why if you see, here you wrote E2 by E1, right? E2 by E1, if you observe, E1 also I wrote the amount of flux that is getting induced. We never took E1 as the direct alternating EMF because they both are same. So, yeah. So E1 can be taken to be the EMF across the primary coil and E2 can be taken as the EMF across the secondary coil. Then E2 by E1 will be equal to output EMF by input EMF or N2 divided by N1. Now, this ratio N2 by N1 has a name. Okay. That is the number of turns in the secondary to that in the primary is called as turns ratio. It's called as the turns ratio of the transformer, or it is also called as transformation ratio, because N2 by N1, not N1 by N2. N2 by N1 is called as the turns ratio or transformer ratio. Is it very clear? Now, when one minute. Now, when I say E2 by E1 is equal to N2 by N1, for it to be called as a step down transformer, then what should be the relation between E2 and E1? Step down transformer. E2 should be less than E1. Output should be less than the input. When E2 is less than N1, can I say N2 is less than N1? So what do you conclude? For you to design a step down transformer, what are you supposed to do? You need to make the number of turns the secondary coil to be less compared to the primary. That's also it. Okay. Similarly, if you want to have a step up transformer, then E2 should be greater than E1, then N2 should be greater than N1. If this happens, you call it as step up transformer. If this happens, we call it as step down transformer. Okay. So the equation one, this is there, no? You can say that it has been derived using the following three assumptions. They'll ask you what are the assumptions that are followed in the case of transformer. This would be a 1 mark question. So what are the three assumptions? First assumption is the primary resistance, the primary coil's resistance is there, right? It is considered to be small. When primary coil's resistance is small, you can say that the current is also small. So these two are assumed to be small. So the primary resistance and the current are assumed to be small. Second is you are assuming that the same flux is linked with both the primary and the secondary windings, and the flux leakage is negligibly small. And the flux leakage is negligibly small. And third is the terminals of the secondary are open and the current taken from it is also very small. So that's what we started the derivation with. You remember? The secondary coil is not connected to the load. So it is under open condition. So all these expressions are derived under these three assumptions. Right? Now we will try to derive. So we derive the relation between the EMFs and the number of turns in the case of primary and secondary. Now we will derive currents in primary and secondary, assuming that the transformer is ideal and there is no energy loss. So if there is no energy loss, what can I say about the input power and output power? They both are equal. Input power is equal to output power. But how do you define electrical power as? It is defined as a product of the EMF or voltage multiplied with current. So E1 into I1 will be equal to E2 into I2, where I1 and I2 are the currents in the primary and the secondary coil respectively. So I1 by I2. So what I can say is E1 I1 is equal to E2 I2, which implies I1 by I2 is equal to E2 by E1. But E2 by E1 is how much? N2 divided by N1. I1 by I2 is equal to N2 by E2 by E1 is equal to N2 by N. Is it clear? So from here, an important conclusion that we can draw is, if you talk about a step-down transformer, step-up transformer, it will step up the voltage, but at the same time, it will step down the current. Because they both are inversely proportional. That's what this mathematical expression says. Right? So a step-up transformer steps up the voltage, but steps down the current exactly in the same ratio. Similarly, the step-down transformer will step down the voltage, but step up the value of current exactly in the same ratio. Is it clear? Next is the efficiency of a transformer. Obviously, efficiency is defined as the output power divided by input power multiplied with 100. So efficiency of a transformer is defined as the ratio of output power to the input power multiplied with 100. Okay. Now see, if you take the efficiency of a real transformer, it is fairly high, which is somewhere between 90 to 99%, though it is not 100%. Okay. Now the question is, we assumed that the energy loss is zero and the current flux is getting completely linked and the resistance and current are small. But in reality, what will happen is there will be some energy losses that are taking place in the transformer, and we need to figure out a method of how to reduce those energy losses. So there are different kinds of energy losses. This is also a question that is asked of. So what they will say is, mention all the energy losses that are possible in a transformer and how you rectify it. The first one is called as copper loss. As the name suggests, copper and another. It is the wire that is made up of. So generally, if you take copper, it has some amount of resistance. And when current is passed through a resistor for a fair amount of time, what will happen? There will be heat generated. Okay. So there will be some energy that is lost due to the heating of copper wires used in the primary and the secondary windings. And the power loss is given by the expression I squared R. But how will you minimize it? You can minimize it by using a thick copper wire of low resistance. Why does a thick copper wire has low resistance? Because R is equal to rho into L divided by A. R and A are inversely proportional to each other. Means if the area of cross section is more, resistance will be less. Is it clear? Second is eddy current loss. Okay. So eddy current is the eddy means the currents which flow in the circular loops. Okay. So what will happen is, if you see the kind of source that you have connected to the primary, it is an alternating one. So the alternating source will create an alternating magnetic flux, which induces eddy currents in the iron core, which leads to some energy loss in the form of heat. So eddy currents will lead to some amount of energy loss in the form of heat. And to reduce this loss is the reason why we are using the laminated iron core. Remember in the beginning we discussed why we are using a laminated iron core. A laminated iron core is mainly used to reduce the eddy current loss. Is it clear? The next point is hysteresis loss. If you observe, the core that you are using is a soft iron core. So iron core, wherever ferromagnetic substances are linked with inducing magnetism, there will be hysteresis, means lagging. Okay. The alternating current that is getting carried in the iron core undergoes cycles of magnetization and demagnetization. When this is happening, right, work is done on the iron core in each process, and that energy is lost in the form of heat uptake. And this loss is called as hysteresis loss because there is always a lagging in the process of magnetization and demagnetization because of iron. Ferromagnetic substance. If suppose you had used a paramagnetic substance, maybe hysteresis loss would have been less, but eddy current loss would have been more. Because eddy currents are mostly generated in paramagnetic and ferromagnetic substances. Okay. And how will you reduce it? By using core material having less hysteresis loop or a narrow hysteresis loop. So if you are able to use an iron core which has a narrow hysteresis loop, you can reduce this hysteresis loss. Okay. Next one is flux leakage. So magnetic flux produced by the primary coil will not get completely linked with the secondary coil because there will definitely be some leakage that is happening into the air medium. But how will you reduce it? You can reduce it by taking the primary winding and secondary winding on top of each other. If you create this kind of a device instead of having the primary this side and secondary this side, then you can reduce the flux leakage also. Okay. See, this humming loss is actually not a part of your syllabus. But as the name suggests, no humming loss means you'll be able to hear a sound. Okay. Till now we saw only heat getting lost. So except the fourth point where flux got lost. Correct? So when you talk about this humming loss, generally when the transformer works because of the alternating current, its length will change. It will get its length will increase and decrease due to a property called as magnetostriction. So magnetostriction அப்படின்றது என்னன்னா, it is the process where the length of a material will change due to magnetism. Okay, and when this kind of a process happens, there will be a humming sound that will get generated. So some of the electrical energy is now neither lost in the form of heat or light, but it is lost in the form of sound. So generally, how you can reduce the sound is depending on where you install the transformer. Similarly, what kind of an acoustic treatment you're able to give. All those things are taken into consideration. If you can use some acoustic materials which can actually absorb the sound, then you can reduce the sound emissions. But as I told you, it is not a part of your textbook level. So I added as an extra point. So I hope you understood. This is all about a transformer. This is a very, very, very important topic. I know it is slightly lengthy, but yes, that's how it works. Okay. And the last topic of this chapter is LC oscillations. This is the last topic. Okay. So what does LC oscillation mean? Now we are going to discuss. If you see, in reality, let's say you have FM or AM. What is FM? FM is called as frequency modulation. AM is called as amplitude modulation. So basically, I told you, right, this chapter, most of the applications will go for communication system. So what will happen is you have a message signal. See, for example, I'm talking, right? I'm talking to you guys. Maybe my voice is audible in this room, that's it. It will not even be audible to the people in the other room. But if I use a device where I want my voice to get transmitted to longer distances, generally what happens with FM? Somebody sitting in the radio station, they're talking. How is the signal getting broadcasted to your house? Means it is carried to a longer distance. How is it happening? Because message signals are generally weak. So if you are able to mix this message signal with another signal which is called a carrier signal. So carrier என்றது என்னன்னு பார்த்தோம்னா, it is a high frequency signal. When you mix a message that is your voice with a carrier signal, then you call it as modulation. And at the receiver's end, what will happen is the carrier signal is removed and only the message is given, which is called as demodulation. So, have you heard of modem? You use the devices that you have put, right? For internet, you use a device called as modem. So, modem meaning modulation, demodulation. Okay. So, this kind of a process actually happens. And why am I talking this in case of LC oscillation? Because if you see, you have discussed about what happens when an AC source is connected across a resistor, capacitor, inductor. Resistor and capacitor, resistor and inductor, or resistor, capacitor, inductor. But we would have never discussed a scenario where an AC source is connected across L and C. So that's why the name of the topic is LC oscillations. Meaning, I told you about this high frequency carrier signal, right? Huh? So I told you about the high frequency signals, right? Carrier signals. Who will generate? So the ones, the machines or the devices which are able to generate those oscillations are what are called as LC oscillators. So that's why this topic is called as LC oscillation. It is a completely theoretical topic. There is no mathematical part that I have to explain. So basically what happens is you will have an inductor and a capacitor connector. So there is no AC source at all. So there will be an inductor and there will be a capacitor. So the capacitor will be fully charged. So when the capacitor is fully charged, can it start behaving like a battery? So can I say a fully charged capacitor acts like a battery? So when it acts like a battery, right, then the capacitor will start getting discharged and it will start inducing an EMF across the inductor. So what is happening? Slowly the capacitor is losing its EMF, whereas the inductor is gaining EMF. So there will be a particular point where the capacitor will be fully discharged, means all the energy that is associated with the capacitor is lost and it will get stored into an inductor. Now what will inductor do now? Inductor has the EMF. That inductor will start charging the capacitor again. So you're able to understand what happens? So initially, when the current is zero, the capacitor is fully charged. So after that, what will happen is the capacitor is slowly getting discharged, as a result of which flux is linked with the inductor, and due to the change in flux that is happening, an EMF is induced across it. So after a certain point, the capacitor will be completely discharged and the inductor will be having the complete EMF. Again, the inductor will start charging the capacitor. Then some amount of capacitance, some amount of charge will be left here and some amount of energy will be left here. Again, what will happen? The inductor will completely charge the capacitor and this will not have any EMF. So it's actually a change of cycle. So capacitor is creating EMF here and the created EMF is again given back to the capacitor. So it keeps running in a loop. Okay. So when it keeps running a loop, you're able to see the energies that are associated. So here, capacitor will store the energy in the form of electrostatic field. So electrostatic energy is initially the complete energy that is present in the system. Then what is happening? Partially electrostatic and partially magnetic. After a point, completely magnetic and zero electrostatic. After a point, partially magnetic, partially electrostatic. After a point, completely. So this original situation has come back again. Again, the same cycle will repeat itself. Okay. By this kind of a process getting repeated, there will be an angular velocity. There will be an angular frequency of 1 by root LC that is getting generated. So by adjusting the value of L and C, you can generate the desired value of the carrier frequency that you want. Or I can say F is equal to 1 by 2 pi root LC. It is something similar to the formula of an RLC circuit in resonant condition. So this is what happens. As I told you, it is a completely theoretical part, which you can read it from here. So there are two important topics that we discussed today. One is called as transformers, and the second is called as AC oscillation. I remember I had not explained eddy currents to you. So we will see what are eddy currents.
I would like to do another demonstration of eddy currents and the resulting magnetic braking that will occur on a pendulum. So what I have here are
So you're able to see your device, right? So eddy currents and magnetic braking of a pendulum. So what happens is when you have a magnet present, okay. So in that magnetic region, if you take an iron particle and take it closer to it, what will happen? Magnet, near that magnet, you're taking an iron particle. What will happen to it? It gets attracted, right? So because it is a ferromagnetic substance, but instead of taking a ferromagnetic substance, if you take a paramagnetic substance in that. If you take a paramagnetic substance closer to a magnet, we don't get attracted. Okay. So that is why if you see,
I would like to do another
they would have used
demonstration of
a
eddy
demonstration
currents
for
and the
this.
resulting magnetic braking that will occur on a pendulum. So what I have here
So you're able
are
to see two magnets. So between those two magnets, they will see what will happen when the
magnets.
paramagnetic.
Okay, so this is like the north pole here of this magnet and the south pole here of this magnet. So there's a fairly uniform field in between here, and these are actually fairly strong magnets. So if I actually put a piece of steel in here, if this were a piece of steel, it would stick,
So
and
if you
I
put a
probably
steel, what
wouldn't
will
be
happen?
strong
Steel
enough
is
to
a
pull it apart.
paramagnetic substance. Get attracted. So instead of putting a steel,
But
we
what
have
I
a piece
have
of
here
aluminum.
is a
See what
piece
will
of
happen.
aluminum. Okay, so
Aluminum
aluminum
is
is
paramagnetic in
paramagnetic,
nature.
so it is
Are you able
only
to see that?
weakly magnetized, so it's not really attracted to the magnet.
No.
Okay, so I also have two other pendulums. Okay, this one has slots in it,
So are you
and
able to
this
see
one, the
that?
slots go all the way to the bottom.
There are different kinds of pendulums that are used. So it is the same aluminum thing. One is looking like what do you call that? For frying and all we use. It's completely rectangular. Second one is having slits, and the third one is looking like a comb. Means it is open at one of the ends. See what will happen when all these three materials are actually passed through this place.
So there's no connection along the bottom. Okay, and any of these I
So
put
you're
in
able to see
here
the
will
swinging.
freely swing.
Obviously, it is going to swing. And why is it swinging? It is because of gravity.
Okay, so now let's see what happens
Now,
when
if you pass,
I
the
try to
same thing, you're
swing
releasing it under the gravity only, but as soon as it passes through the magnetic field, see what will happen.
this one through the magnetic field. Okay, notice how it
is not
breaks
swinging.
and
Why?
stops. Now, if I did the one,
Initially, what happened when the magnet was not present, it was swinging continuously. But when you place the magnet, when you pass it through the magnetic substance, immediately right? It is because of eddy currents. Okay. Next one you saw with the slots, right?
With the slots.
So you're able to see this with the slots now. So it is closed at the bottom also, but you have openings. Now what will happen to this is, what do you expect? Will it swing or will it stop? Yes, sir. So
We
what
see it
is
also
happening? Here
breaks and
also it
stops.
is
Not
stopping.
quite as quickly.
It is going to a slighter distance and stopping. Whereas the previous case, what happened? It came to instant rest. Whereas here it is slightly going to the left and then coming to rest. Okay. What about the third one? What do you think will happen to this?
And finally, the ones with the grooves so that there's no connection on the bottom.
Is not worried about the magnetism at all.
Swings
So
free.
what happens is,
Okay, what is happening is that as this one
when it was
is
entering
swinging
into
into
the
the
magnetic
field,
field, inside the material, there was change of magnetic flux taking place. When there is a change of magnetic flux taking place, what will happen to the value of current? What will happen to the flux? Change in magnetic flux is taking place. EMF is induced, and that EMF induced will in turn cause a current in the material, and that current is what is called as eddy current. And when can you observe these eddy currents to exist? When you talk about, so you can talk about a ferromagnetic also. When a paramagnetic or a ferromagnetic substance is passed through a magnetic field, then you can say that there is so this is the magnetic field. Okay. So into this magnetic field, what has happened is this aluminum material started swinging. So when it started swinging, there was an increase in the amount of area that was entering the magnetic field. Is that right? So when I put an into mark like this, which pole is the paper? Paper is the south pole, and who are we? We are the north pole. So when it is entering the field, then when I say flux is increasing, then what pole should get generated on the side which is facing us? Flux increases, same pole. So north pole would have got generated. When north pole has got generated, what will happen is there will be anti-clockwise currents which will get generated in the loop. And these circular currents are what are called as eddy currents. Or sometimes they are referred to as circular currents also, but the more technical name that we use is eddy current. And this loss is what we spoke in the case of transformer, eddy current loss. It has happened because you're using an iron core to be ferromagnetic. So ferromagnetic substance, eddy currents will get generated. It's logically simple. Why do eddy currents get generated? Because of the change in flux. That's it. So, yeah. So to conclude the whole story, the circular currents that are getting generated in a paramagnetic or a ferromagnetic substance when it is trying to enter the magnetic field and there is a change in magnetic flux taking place is what is called as eddy current. Am I clear with this? If you are able to connect what is eddy current loss, so in the eddy currents in the generator, in the eddy current there will be a heat, and that heat is also a loss which will occur in the iron core. That is why to avoid it, you are using a laminated iron. Are you able to connect the dots? And if I have to be more specific, right, this eddy current principle. So now you can ask me, why did the rod with an opening, there was something like this, no? The second one that we saw, it went to a certain distance and then stopped. Why did that happen? Because you have this opening, right? And due to this opening, the amount of current that will get generated will be comparatively less when you compare it to the previous scenario. Whereas in the case of open structure, like when you had this comb-like structure, right? Why didn't it stop at all? Because currents cannot be in circular loop as you have openings here. Breathe out. So in the first case, since there are no openings, more amount of current was generated. In the second case, there were openings, but since the loop was there, it still had some amount of eddy current existing. Whereas in the third scenario, complete opening irukkiradnala, that's what happened. So yeah, and this is the idea that is used in braking system. See, for example, if you go to these theme parks and all, you have these roller coasters, right? The roller coaster, we don't go there. When the roller coaster is coming down, you can observe that it will get slightly slowed down at this point. The reason for it to get slowed down is because they use this principle of braking system. Or else what would have happened is you will face a lot of jerk and it might injure you. Wait. So these are all the systems. It's all about eddy current. Now we can connect both the concept of eddy current and eddy current waves. So with this, we are done with the 7th chapter also. So Monday you have a test, right? 4th chapter. Monday, Saturday you have 4th chapter test. Okay. See, second volume will go faster. Only 9th and 10th chapters are slightly big, so it does not rush through. So what we can do is electromagnetic waves is also small, maximum 1 class or 2 classes. It's a very small chapter. What we can do is you guys utilize this week to prepare and work on the backgrounds. I won't want to rush. Tomorrow will stop. Tomorrow will not have a class. You can utilize it for preparing for the upcoming test. Moving charges and magnetism, putting open. After that, what I'll do, they'll conduct some more tests also. 5th, 6th, 7th test. So next week, what we can do, we'll try to have some paper discussions. Current electricity, electrostatic potential. I will discuss the paper. I'll discuss the paper. I'll discuss there will be some more important points that come out. That's next week discuss. Then we will go to that electromagnetic waves. Yeah, electromagnetic waves. Electromagnetic waves is not important for this volume. It's important for the next volume. So next volume, before we step into it, yeah, make sure that you're thorough with these chapters. Those who are online, could you hear me?
Yes,
sir.
Okay, so tomorrow we'll not have a class. Saturday, you prepare for Saturday's test. And next week, Monday is our test. Monday, so Monday, I relax. Tomorrow I'm there, but I'm giving a break only for the study. Monday I'm not there. So Tuesday and Wednesday we will have paper discussions. Of Tuesday second bola, Wednesday we'll go for third, and the other one will go for fourth. In the meanwhile, you prepare for the 5th, 6th, and 7th. Yeah. So work on it. Right. So that's it from my side, and we'll find out. Okay. So those are online also. We'll find out.
So next class Monday, sir.
Yeah, the next class is on Tuesday.
Tuesday, fine.
Okay. So
Yeah,
Tuesday
fine,
we'll start.
Okay,